In this presentation, I show the progress made this semester towards measuring branching fractions of iron 2 ions in the vacuum ultraviolet region. What are we trying to do? Our goal with this project is to provide atomic reference data for singly ionized iron, Fe2, in the vacuum ultraviolet range by measuring its emission spectrum. This data is important for interpreting spectroscopic observations of astrophysical objects using instruments such as the Hubble Space Telescope Imaging Spectrograph. Current research is hindered by the fact that of the 3,000 some emission lines in iron 2's spectrum in this region, only 21 have measured transition rates and branching fractions. Our work will make stellar spectroscopy data more readily usable and has applications including modeling stellar atmospheres, as well as determining the compositions of stars and accretion disks. First, we must understand how atoms radiate light. Electrons can only orbit around atoms at discrete energy levels, much like how a person can be on the 2nd, 10th, or 3rd floor of a building, but not the 2.5th floor. If in an excited state, the electron will quickly jump to a lower energy state, emitting a photon whose energy, delta E, makes up the difference. The photon's energy and wave number, sigma, both relate inversely to its wavelength, lambda. Since the electrons can only have discrete energies, the atoms can only emit photons of discrete wavelengths. One could liken a radiating atom to an orchestra, and it's our job to determine the sheet music of every instrument entirely by ear. In order to transcribe this orchestra, we use an extremely sensitive tool known as a vacuum ultraviolet Fourier transform spectrometer, which can observe emission lines ranging from 135 to 1,150 nanometers. The lines in this region of iron 2's spectrum are extremely dense, which less sophisticated equipment like diffraction gratings aren't capable of resolving. This is a large part of why so little research has been done on these lines. The VUV-FTS is able to achieve the necessary resolution to observe these lines by seeing how the light interferes with itself when sliding a mirror back and forth. As the source light, composed of many different frequencies of light, enters the FTS, it's split by a mirror. One half reflects back off of a mirror at a fixed distance, so that half of the light always travels the same length. The other half of the light reflects off of a mirror on a sliding track, which can move closer or farther from the splitting mirror. This causes the length of the path for this half of the light to vary, which changes its phase relative to the light with the fixed path length. This difference in phase is observed when the two beams are recombined and focused onto the detectors, which record how the intensity of the light varies with the mirror's position as an interferogram. This is the raw data from which we will determine the iron 2 spectrum. Now, what do we do with our data? Once we have the interferogram, we take its Fourier transform to get the emission spectrum. A Fourier transform decomposes an input function into its component frequencies and specifies the intensities of those frequencies. If you took the Fourier transform of an audio clip of a C major chord where the G was louder than the C and the E, you'd get 3 spikes. 2 would be spikes of some height at the frequencies of the C and E notes, while the third would be a taller spike at the frequency of the G note. This is exactly the mathematical tool we need to study the frequencies of light that were emitted by the source. Where we have spikes, our detector counted photons with the corresponding wave number, meaning a transition happened with an energy difference corresponding to that photon's energy. The integral, the area underneath the spike, is the intensity with which the light was detected. When a particular frequency of light is more intense, that means the transition it corresponds to happens more frequently than a transition with a less intense line. This leads into what brings us here today, branching fractions. Separately, the lifetimes of the levels we're concerned with were measured. These characterize how long an excited electron will stay in that excited state. We then get our branching fractions from the STIS. As I mentioned before, we can determine the intensities of emission lines using an integral. Well, the branching fractions for a particular transition is the ratio of that line's intensity to the sum of the intensities for all the transitions from that upper level, and corresponds to the relative likelihood that the electron will decay to that particular lower level. In order to make sure that our measurements are consistent, we need some form of radiometric calibration. In our case, we use a deuterium lamp. Once we derive our branching fractions from the intensities of the lines, we can combine them with the level lifetimes to calculate their absorption and oscillator strengths. To radiometrically calibrate our measurements, we measure the spectrum of a deuterium lamp light source first. We do this at the beginning and end of runs to ensure conditions haven't changed significantly, and to account for the detector's varying sensitivity for light of different wave numbers. Once we have our response curve, we filter and smooth it before using it to calibrate our data to reduce the noise that could be introduced. The curve can then be used to determine the correct intensities of our iron 2 spectrum. After the calibrating deuterium spectrum is measured, we switch to the sample that will emit the spectrum we actually want to study, in our case, iron 2. To actually make the source glow and emit our desired spectrum, we apply a voltage across an iron hollow cathode inside an evacuated tube that's filled with a buffer gas, such as argon or neon. We then identify the emission lines with atomic transitions and proceed with our calculations. Before we look at our results, what's been done so far? Well, not much. Two previous works used were by Pickering at Imperial College in the early 2000s, studying 21 sets of branching fractions for emission lines ranging from 226.1 to 330.4 nanometers. Ferguson at University of Wisconsin published branching fractions for 20 levels in a narrower range back in 1996 as well. We can test the consistency of our calibration by comparing branching ratios with previous measurements. If the calibration is consistent, we expect a horizontal line. If the calibration is not consistent, there will be a slope. This figure shows that our calibration is consistent with the measurement of Ferguson's, but the work of Pickering's is not consistent with either Ferguson's or our measurements. This means that we cannot rely on Pickering's spectra either in our new analysis or to confirm our calibration in the shorter wavelength region that wasn't covered by Ferguson. Now, what did I bring to the table? I've started calculating branching fractions for levels in various detector runs. I've then compared and contrasted these with previous work. I've meticulously combed through spectra to pick out weaker lines that don't get detected automatically by our software. I've also written Python scripts to automate a number of frequent and simple yet tedious Excel tasks. I'm also verifying that our spectrometer's calibration is reliable. Now, how is the project moving forward? Our next major goal is to figure out which levels we simply can or cannot publish about based on the quality of our measured lines, and whether or not our calibration is consistent. We're also reconfiguring some older software to more conveniently analyze our data. That concludes my presentation, and thank you for watching.